Okay, we're jumping straight back into TempConverter. This is going to be part 2 of it. When we left off, we had this little bit of code. We're using some variables here, right? I have Fa, which represents my temperature in Fahrenheit, and then we're trying to convert it to a Celsius temperature using our formula, 5/9 times the temperature that we want to convert minus 32, and all that is in parentheses because we want the subtraction to happen up front. And the variables here are nice, right? Because this allows me a very easy to get to place where I can change my temperature. And you might say, well, you could just do that here. But one thing that the variable allows me to do is I get to reference it in multiple spots. Right here I'm typing, I have Fa, my variable, F-A-H, and here I have it, which there's 2 points. But if I'm editing this, right, if I want to switch temperatures, I only have to change it at 1 point. Now, when we left off, there was an issue. Right? This seems to work with 32 degrees, right? Because 32 degrees in Fahrenheit is 0 degrees Celsius. So when I run my temperature converter, we're going to see our output here, 32F. Right? This is all part of this string here. 32F is equal to 0 Celsius. That looks really good. But another common temperature we know, right, 212 degrees in Fahrenheit should be 100 degrees in Celsius. When I run this, however, it says 212 degrees Fahrenheit is 0 degrees Celsius. So something's not right here. My formula looks good, but I'm just not getting the correct result. And that's what we're going to pick up today, is talking about that. So we've been doing our temperature converter, and algebraically, this expression should evaluate to 100, right? We're going to do the parentheses first, so we take our 212, we subtract the 32, then going from left to right, we would do the 5/9 next, and then we'd multiply that and get to 100. However, in Java, this expression is giving us a result of 0. The issue occurs when 5 is divided by 9. Algebraically, this should be 0.5555 repeating. In Java, whenever 2 integers are involved in a division operation, the result must also be an integer. And integers are whole numbers. What am I saying? Here I have 2 integers. I have 5, that's an integer. I have 9, that's an integer. Integers are whole numbers. When division occurs between 2 whole numbers, 2 integers, the result needs to also be an integer. Okay? If a division operation involving 2 integers would produce a floating point number, we talked about floating point numbers in a previous video and previous slides. This is the terminology we use to describe decimal numbers. Any number with a fractional part, we say it's floating point number. We avoid the word decimal because decimal could also imply the decimal numbering system, what we're used to, that is base 10. But in computer science, we often work in different bases. Binary, which is base 2. Hex, base 6, oct, base 8, so on and so forth. So we avoid this word, and instead we say floating point number, and that's any number with a fractional part. If a division operation involving 2 integers would produce a floating point number, that number is truncated. That is, the fractional part is discarded completely. What are we saying? This 5 divided by 9 evaluates to 0.555 repeating. But it's going to get truncated. And what that means is this fractional part, this 0.555 repeating, just gets dropped entirely. This is not rounding, this is truncation. Right? If we take that 5/9 and we do that division and we get our 0.555, then that gets truncated. It's going to get truncated to 0. And so we're doing 0 times the result of this, leaving us with 0. So it actually doesn't matter what we do here. Right? Any temperature I throw in here, that's too big of a number, any temperature I throw in here, we're going to get 0 because this 5 divided by 9 is giving me 0 every single time. Right? So just a coincidence that the 32 happened to work, right? Going from 32 degrees Fahrenheit to 0 degrees Celsius, that just happened to work. This is why you want to try multiple things, that is multiple test cases. Okay. So with that in mind, what do the following expressions evaluate to in Java? Keep truncation in mind. Excuse me. Right? 11 divided by 2, algebraically, this should be 5.5. But in Java, this is going to get truncated. Truncated to what? Right? I want you to try to work out some of these other ones. 8 divided by 3, 9 divided by 10. Think about what it should be algebraically, then truncate it. I'm going to reveal the answers now. Right? 11 divided by 2 should be 5.5, but we're going to truncate that because it's division between two integers, and the result has to be an integer, so this will be truncated to just 5. This 8 divided by 3 should be 2 2/3, but we'll get rid of that 2/3 part. It's going to truncate to just 2. Right? This 9 divided by 10, 0.9, is going to get truncated to 0. We just get rid of the fractional part. This is not rounding, this is truncation. So with that in mind, we have expressions like these. Right? Keep in mind order of operations along with this. The first thing I would evaluate is what's in the parentheses here. So I got 15 divided by 4 times 2. That 15 divided by 4 is going to be 3 and some change. That decimal, that fractional part, gets truncated to just 3, leaving me with 3 times 2, 6. Here's another one. 6 divided by 2. Well, that's actually nice, even, and clean. 2 will go in there 3 times. I'm left with 3 plus this over here. 3 will go into 7 2 times and some change. We'll get rid of that fractional part, leaving us with 2. So this is ultimately 3 plus 2, or 5. Okay? I want you to try these on your own. Right? Pause the video, get out some paper. Use what you know about order of operations, but also keep truncation in mind and see if you can evaluate these. Now is a good time to pause because I'm about to click and reveal the answers. Why don't you see how you did? So the question then becomes, what about this program? Are you telling me that I just can't convert from Fahrenheit to Celsius? Well, of course you can, because we're talking about computers here, and we use computers all the time for these types of conversions. That's where double comes in. Double is one of the primitive data types. Recall there are 8 primitive data types. I'm asking you to know 4. This is one of the ones I'm asking you to know. It's a primitive data type that is capable of storing floating point numbers, decimals. Here are some examples of its use. Here I'm declaring a double called my variable, not assigning it a value, not initializing it, just declaring. I'm creating a box, and the way we'll refer to that box is my variable. Here I'm creating a double called hippo and giving it a value right away. Notice that it's 17, right? That's an integer, that's a whole number. I can save integers or whole numbers into these variables. Keep in mind, however, that once it's in this variable, it'll be treated as 17.0, right? If I was to print hippo, we would see in the console and the output 17.0. Here I have double x, given the value of 3.14. We actually see this is a floating point number, perfectly fine. And then we see double number, negative. We could have negative doubles in the same way that we can have negative integers. So double is a primitive data type that can be used in the declaration of a variable. Okay, why do we talk about double? Well, as long as one of the operands involved in the operation is a double, the result will also be a double. This is a way to avoid truncation. What am I saying? 2.0, this is a double, right? Even though it's a round number, it's a double. It's got this fractional part. This 2 here is an integer. However, here I have a calculation where one of the operands, this 2.0, is a double. That means 2.0 plus 2 is not just 4, it's 4.0. As long as one of the operands involved in the operation is a double, that is, it has a fractional part, the result will also be a double. We see that here. If I take this 4 divided by 7.0, well, this 7.0 is a double. This 4 is an integer. One of the operands is a double. The result will be a double. So this prevents the truncation from happening. Same thing here, and then same thing down here. This one's a little interesting. I'll take a look at this last one. 3 divided by 4. I have an integer. I have an integer. I have division between two integers. This should be 0.75. It's going to get truncated to 0, right? And then when I take that 0 and I multiply it by 3.0, I don't get just 0, I get 0.0. Why? One of my operands is a double. So here it is breaking that apart, right? This 3 divided by 4 is going to truncate to just 0. I'm left with an operation where I have a double times an integer. Because one of the operands is a double, the result has to also be a double. This is a test question if I've ever seen one. Okay, so with that in mind, doubles to the rescue. Right? Let's flip back to our temp converter and see what we can do here. My problem is occurring right here with this 5 divided by 9. I have division between two integers and it's getting truncated to just 0 and multiplying everything by 0, giving me 0 always. What I can do to prevent this truncation is to make one of these a double, at least one, right? It doesn't matter, pick one. I'm going to try it with 5. I now have 5.0 divided by 9. Because this 5 is technically a double, I won't get truncation here. I will get the correct result of 0.555. But now notice, this is mad at me. Why? This right-hand side, because I have a double here, ultimately the entire calculation is producing a double, right? We'd come in, we would do this first because it's in parentheses. We would subtract our temperature in Fahrenheit. Why don't we go back to like 212? I would get 180 here from the subtraction. We would then do the division because it has equal precedence with the multiplication, but appears first. We would get 0.5555 repeating. I would then multiply that 0.555 repeating times 180. Okay, well that last operation, I have a double times some type of integer, whole number. Because one of the operands is a double, the whole result, this whole calculation I have highlighted is producing a double, and I'm trying to save a double into an integer. Simply put, you can't do that, right? You cannot save a double, a number that could have a fractional part, into an integer, a data type that can only store whole numbers. It's a simple fix. We can just change the data type. Okay. So let's try this out first and foremost. Right? I'm going to run my program. I have a temperature that we know and love, 212. We know it's supposed to go to 100 degrees Celsius in this conversion. So I'm going to run my program. And there we see it. Our 212 Fahrenheit is equivalent to 100 degrees Celsius. So double is really nice because it allows us to store numbers with a fractional part, which kind of begs the question up here, why aren't we using double here? And the answer is, well, we probably should be, right? Because something like temperature, a temperature in Fahrenheit, well, it can have a fractional part, right? I used very round numbers here, like 32 and 212, 212, but we could have a fractional temperature. We could have something like 73.2 degrees Fahrenheit. Let's try that. Right? My 73.2 degrees Fahrenheit is 22.8 and some change. This may be a little bit wonky. Don't worry too much about that. But our program is now working. Our problem was truncation, and we're preventing that by changing one of our operands to a double. Now, I told you it doesn't matter which one. It could be the 5. It could be the 9 that we change. You could do both. Right? I'm going to run this, and we see that we get the exact same result. So it doesn't matter as long as one of the operands is a double, the result will be a double. So does this mean you should always use double? It kind of begs the question, why don't we just use double always? Right? If integer has this setback, let's just use double always. And the thing is, when a variable is declared in Java, there's a certain amount of space set aside based on the variable's data type. Right? When you create that box, it has dimensions effectively. You're creating a box and you're saying, I can only put integers in here. Well, you're also dictating how big the box is. Right? As it turns out, double variables consume twice as much space as integer variables. Therefore, it is inefficient to use a double variable whenever an int variable can accomplish the same task. You should always try to use the appropriate data type. For us in this class, the space difference, we're going to talk about what the exact amount at some point, But the space difference is not a big deal. We're only using just a handful of variables. But when you get into what we call big data, right, you're processing credit cards, you're sequencing the human genome, right? We're talking large amounts of data, consuming twice as much data, right? Think about a credit card. Each credit card being an integer versus each credit card number, I should say, being a double, right? That is a lot of data, and this inefficiency becomes a big deal there. Okay. One more last thing to kind of talk about, valid and invalid number literals on this topic of double and int. Valid numbers include 2,200, 2.2, right? I got these extra zeros that won't really matter that much, but this is just a double, a fractional number. Here I have 2.2 e minus 2. I want you to pause and think about what that is. This is scientific notation, right? So we can actually have scientific notation. We're going to use that very soon in our program. The only thing that's really invalid that you may encounter typically as a normal human on this planet is a number with a comma, right? That's not going to work for us. And just to quickly show you that, I'm going to create some little nonsensical variable here, right? I can have a double temp. I'm going to delete it in just a moment, don't you worry. And so, you know, we could have 2,200. We could have 2 point that. Why don't we print that off real fast and see what it looks like? And I'll show you that those trailing zeros don't really matter. So this should be the first number that shows up in my program. Right? Those trailing zeros that I put here, they didn't ultimately matter. We can have scientific notation. Shows up there. I think if we maybe lower this number, we actually will get the precision. Maybe not. Not important. Okay, so we have scientific notation. The only thing that we can't do is that. You see IntelliJ is mad at me right away. If I try to run this, it's not going to do anything. It's just going to yell at me, and I'm going to be sad. Okay, let's recap. The process of discarding the decimal portion of a number is known as truncation. Double is a primitive data type capable of storing blank numbers. I'm looking for floating point numbers. If you say decimal, I'm not going to be mad. I'm just going to be disappointed. In Java, what does this expression evaluate to? Right, keep in mind in Java, we got some division, but truncation could occur. Now might be a good time to pause it and maybe try to work it out on paper. Let's talk about our solution. We got 5 divided by 3. 3 will go in here one time with some change. Well, that fractional part is going to get truncated, leaving me with just 1 over here. Let's do this side. 9 will go into 16 one time with some change. That fractional part is going to get discarded, so I'm left with just 1 plus 1. In Java, a single operation will produce a double as long as blank. A single operation will produce a double as long as one of the operands is a double. At least one, right? If both are, it's the same thing. In Java, what does this expression evaluate to? All right, be careful, I've mixed in a double here. Now might be a good time to pause it if you want to work it on paper. I'm going to pause it and take a drink. So my first question would be, what do you evaluate first? Well, looking at this, we have some division. We've got some addition, but that's it. So we're just going to evaluate the division from left to right. This 8 divided by 5 would happen first. That's going to be 1, and we got some left over. A fractional part we'll discard. We'll truncate that fractional part. So this is just going to be 1. Plus, I have 13 divided by 2. Let's execute that. 2 we'll evaluate, or we'll go into 13, 5 times? 6 times and some change. We'll get rid of that excess, that fractional part, leaving me with just 6 here. I then have 6 divided by 3.0. Okay. Now, here's where things get a little bit difficult. 6 divided by 3.0. It's not just 3. 6 divided by 3, that's going to be 2. But because I have a decimal here, a fractional part, a double, the result will be a double. What that means is this isn't just going to, this 6 divided by 3.0 is not just 2, it's technically 2.0. So what I have is 1 plus 2.0. Because one of the operands is a double, right? This 2.0 over here on this side, my result will be a double. 1 plus 2.0 is going to give me not just 3, but 3.0. Again, that's a test question if I've ever seen one. True or false? Int variables consume half as much space as double variables. This is true. We're going to learn at a later date the exact amount, but right now, just know that double consume twice as much space. That's not why they're called double, but there you go. Which of the following number of literals is invalid? Ooh, this one looks a little wonky, right? I see the comma. I'm fairly certain that's the answer. Here, we got an E. That's scientific notation. We did scientific notation, but we use a capital E. And Java is case sensitive as far as we know. So are there 2 answers here? So looking at this capital E, we see that works. That's perfectly fine. As it turns out, lowercase e also works. I tend to like using lowercase e in practice, right, when I'm putting my number in here. The reason being is it doesn't, it helps, it doesn't look like a number, right? This uppercase E, to me, can blend in with numbers, especially once you start having lots of numbers, okay? I think when you make it a lowercase, it stands out a lot more. I have a little bit of a qualm in that it always shows up as uppercase here. That can be really sneaky at times, but at least in my source code, what I can control, I like to use a lowercase e. And as it turns out, this is a valid number literal. Okay, that's going to be it for today. That's the rest of TempConverter Part 2.